All right, welcome. If you're continuing this video series, this is going to be part 3 of task 8 for the NSA Codebreakers 2024 challenge. In the last task, we had identified the elliptical curve functions and we're identifying them with our reverse engineering. In this video, we're going to continue on with identifying the last of these functions and then hopefully see how far we get in this part. None of this is scripted. I don't know how long these videos usually take. I just hop into them and start recording. So granted, if it takes a while, there's probably going to be at least one more part for identifying probably coding and then another one for maybe even exploitation of this or solving the challenge. So hopefully it doesn't take too long. But in this task, we're going to be continuing on with the reverse engineering. So with that, we know that elliptical curve cryptography is mostly done within this function. We had stepped through a lot of it, or half of it, I'd say. We got to the MCC part, or ECC multiplicative part, and kind of stopped, but then identified all those functions within Ghidra. What I'm going to do is actually identify or finish identifying that these are mem copies. So just see if this 3,4 is actually stored here after this function is called. It appears to be stored, but it's actually stored in reverse. Looks like 34C9 is at the end, and that's what was at the beginning. And we can even just compare all of the bytes as long as it wasn't zeroed out. So 34C9, 34C9, and all the way to 2F. So this isn't mem copy, this looks like reverse bytes. And copy. We go on to this next copy. This appears to do something with the memory in place with the static value 20, or just the static value. Probably be 20 again, because that's what this length of bytes have been. I'm going to copy this and then just step over again. Let's keep a mental note that it was C934 and that it ended with 2F. Normally ended with 2F. So if we step over, oops, check out the bytes. Looks like it didn't do anything of point or do anything. So it actually might be checking to see whether it returns correctly. So maybe it's not doing it's doing another comparison at the end, so maybe it's just checking to see if it's maybe a valid of some sort. Maybe it's just greater than a certain value. So we could just name this from copy to check question mark. There's a good chance that this is going to be what's returned. So if we follow it, uvar3 is what is returned at the end. So if we step through compare w0 to 0, conditional set x21 if equals, so x21 is now 1. So if we finish this function, we can check to see that x0 is 1. So that's the return value. So this is just checking to see if our final value is either valid of some sort. It has to be not 0 to continue on. So that's good. So we can continue on to the next call. We're not going to step into it yet because we don't know what's happening. But it looks like we should be at calling B790, which we are. And it looks like we're just passing a memory address, and it looks like it's setting some values. And as we do with all hard-coded values in cryptography, we Google them instantly. So we just search crypto. This value, it might be elliptical curve still, it might not be. I would really like it if it only searched for stuff that had that value, which this one does. It looks like a bug from some kind of crypto suite is throwing this error. If we look around, it looks like that value is set to a register. That might be just a coincidence. Are the other values around it? We could check to see if anything else is also set in memory. Doesn't look like it, so maybe that's just coincidence. Maybe our just adding the word crypto was throwing it off. So let's just search for that hex string. Looks like a lot more stuff is showing up. Panic when profiling AVX2. A lot of issues are showing up. Looks like it has maybe something to do with SHA-256. So let's see if we can find these bytes in here again. That one wasn't there. Did I copy the wrong one? Looks like neither of them are actually in here for some reason, but we came up with something maybe SHA-256 related, which is a hashing algorithm. So we could try adding SHA-256 onto the end, see what comes up. This one pops up again. What if we add 0x? ARM 64 binary sig il on startup. This appears to be our entire structure, so that looks promising. Hop into it. Can I scroll over? Appears to be just our stuff in memory. Looks like it has something to do with, yeah, SHA-256 again. So that's 2 references to SHA-256. Right here in SHA-256 mod.cpp. This loads. Not sure why it's taking so much to load. It is a decent sized file, but it shouldn't be that bad. We're going to back out and go to a different one. Oh, even here's just a CTF write-up that someone else had searched for these bytes. BB67. So it looks like if you find those bytes, a quick Google search shows that it's SHA-256. So we have enough proof to show that this is probably the SHA-256 function or something related to it. But just based on the fact that this is SHA-256, there's a good chance this is SHA-256 init, since that's usually the first function called. So this might be the SHA-256 structure. 256 struct. If we continue on, it looks to be, this has a very similar setup to update, SHA-256 update. And then this might be the finalization, where it's going to copy the bytes from the structure to this memory spot. We could step into it and walk through that, but just based on that alone, we could actually test this with our values in GDB. So we think this is going to be init, so all it should do is really set values in memory. So we grab this memory address, check out and see that it's just set those bytes in memory. Come down to the first one, see that it's going to be using this string, 32 bytes. To test it, we'll have to move these bytes, or test this ourselves. So I'm just going to copy this, do a quick test.python script from hashlib import SHA-256, m is equal to SHA-256. I think that dot init, m.update with our bytes. I'm going to do some Vim magic to help clean this up a little bit. Get rid of these 2 lines. Want to shift v this, %s, get rid of any 0x's with \x's globally. Oh, don't need the %s, just need s. And then I'm going to get rid of white space, \t, I think. Nope. Should just be spaces. Get rid of those. And then I can just get rid of the new lines by hand. P dot, or just print m dot final dot hex, I think. Python 3 test dot py. It's not called init, just SHA-256. Has no attribute final. Let's look up a quick Python example. Python 3 SHA-256 example. Hashlib .update.digest. That works. .digest.hex. There we go. So if we're right on our assumptions after we step through this one, this should just update it. We could look in memory and identify it because a SHA-256 structure is actually very well defined. Maybe I miss. Whatever. We're going to step through it. This should save it here. Is it not this one? Oh, it's not. It's at B8. So yeah, so these bytes here should actually make up the final answer, I think. One of these, maybe they XOR them against each other at the end. Let's just see what it comes up with, because it's not looking at like our value. This should be the final location. X/16, we'll go 32 bytes at this location, and it does appear to be exactly that. So C028E602. So we've identified one of the functions so far, or some of the functions. So this appears to be SHA-256 update. This looks to be SHA-256 final, or digest, whatever you want to call it. So this appears to be based off of OSStack48, and OSStack48 was sent in from our ECC. So it's SHA-256ing whatever comes from our ECC function. So that's good to know. Where does it use it at? It uses it in C8 here, and then down here as well. This might just be overwriting it though at the end. So 2.8 goes to C8. C8 is used right here. So it's also passed into this function. Socket buffer length equals socket buffer length plus, so minus 6 0x60. So maybe it's ignoring the 0x60 bytes it already used within the ECC function. I don't think it used 60 though. If we remember, it should have used 0x40, because it used 20 here and 20 here. So it's possibly ignoring another 20 bytes. Not sure what's going on there yet. Unless did we misidentify one of these static values? It should both be 0x20. Buff plus 0x20. 8 times 4 should be 0x20. Yeah, so I don't think it should be, so maybe it's just increasing it or decreasing it by 0x60 for some reason. Yeah, it's even here it's going buff plus 0x60. I'm not seeing a socket buffer. Oh, so here, 40, 48, 50, 58. And it's doing a comparison at the end. So maybe the structure of this packet is that these 0x20 bytes are some kind of checksum, and that's what we had to authenticate with at the end. So with that, we can dive into this function. So it looks like this should be our hashed ECC value. Not sure what that is. Param1 is a stack value, if I remember correctly. Yep, so that's probably nothing yet. It's not used yet. It's 176 characters in length, which is an interesting size, as this value right here should only be 32 bytes. It looks to be doing some kind of memory manipulation. It's accessing some kind of key in memory. Not sure what that's for yet. We could check these bytes as well. We could do C3, 7C, 777B, F2, 6B, 6F. Not seeing anything for it, so maybe it's unique. It doesn't appear to be any kind of ASCII value. I think that shouldn't be unique, I don't think. Let's try it again. Anybody's try 1, 2, 3, 4, 5, 6, 7. Let's try one more byte. C5. Let's try just without the 0x. There is this one. This just appears to be a coincidence. What if we add, because right now it's stored as an array in our memory. What if it's stored as an array in whatever other place we're trying to look? Well, it wasn't a math box. Oh, we got a hit with Ringedal Xbox, S-box. And we also got a hit with AES. C37C777B. So this actually appears to be the exact S-box itself. So it appears to be AES S-box underscore S-box. So this function must be some kind of AES init, or AES init question mark, because it's using the S-box in some kind of capacity. If you don't know what that is, we could do a quick identification. So how AES works is that you're going to take a IV and a key and make a shared, not shared, but It's a block cipher that uses the SBox to create a unique value or lookup table. So SBox is pretty much just a lookup table. And it's unique enough where we could go through all the bytes and identify, see if it's corrupted in some way. So if it's off even just a little bit, there's a chance that some kind of AES exploit could work. But I'm just going to give you, or tell you right now, that it's not, or it's not invalid. We know the SBox is going to be 256, so we could set this up. Doesn't look like there's anything after. These values above might be something related as well. We're not sure what's going on there. I don't think it's used in this function. We could look through it later though, or just identify it. But with that, we could try to see if what it's doing is just creating an AES initialization, because there's a good chance it is. So maybe this is like if we looked at AES example C, a tiny AES is the first thing that shows up. This could be just AES init. We're not sure if we're using CTX, CTX IV. We're not sure what kind of version AES we're using yet, like 192, 256. I don't think the SBox tells us. It might. It looks like it ends at... I think the SBox is the same no matter what. There should be an inverse SBox somewhere, so if we look for the bytes 5209. Actually, the inverse would only show up if it's trying to do the opposite operation, which AES is a two-way operation, so if you use the SBox to encrypt, you should use the inverse to decrypt. Here's the initialization function. So it looks like it should do a couple XORs. Looks like there is a XOR down here at the end within this do while loop, and it looks like it's just doing 4 bytes at a time instead of 1 byte at a time like this one's doing. It also is XORing by 0xC3, which I don't see that one in here, but that just seems like an interesting value to XOR by. But more or less, we could, just to save some time because this video series is getting a little bit longer, this is going to boil down to just being a AES initialization function. We'll check that in memory later just to see what it kind of looks like, because it's not going to be a directly typical AES implementation as far as I'm aware, but it is just an AES implementation. So if we AES init into 208, there's a good chance 208 is then our AES. It's not called the key. Might be called the key. Key is what you pass in, but I think after it gets SBoxed, it turns into something else. SBox at P. Oh, we'll just call it the key for now. So then it's going to go into this function. So we have an end buffer, our socket buffer length, socket buffer plus 0x60, socket buffer length again, 15.8, which is going to be 18, which we're not sure if is anything we could actually step through in GDB to see what's going to be there. I think we're actually done with the nano ECC for now. We will come back to it probably. Where are we? We should be right after the final function. So we're going to step through. This first branch should be right here, I believe. 2380. So if we grab this value, there's a good chance that after we step through, look at this in memory, this is going to be our AES key of some sort. The length looks to be a little bit longer than 256, 60 bytes longer. I think, yes, this should be, no, that's 127. 127 plus 0x, or 64, there's 128, plus 64 should get us to 192. So we're actually probably doing AES 192 just based on the length of this key right now. So that's good to know. Do context, step through. We come up here, looks like where we're saving it, what our remaining size is, what our data is. The size of the data, our AES key, is that it? Should be one more right there. That might just be, interesting enough, it might just point to our AES key as well, or right before AES key. Let's do x slash, go to the history. FE1B8 actually points to the SHA-256 value. Yeah, because here's the final key. I think this is the SHA-256 structure. Might just be memory. But our AES key should be the next parameter as well. So step in, we're going to rename some of the parameters. AES key. Not quite sure on parameter 5 yet. Parameter 4, let me do that. Context, parameter 4 should be a length. Parameter 3 should be our data. Parameter 2 should be our length. Length 2. And if everything's been following the same pattern, this should be our out buffer. So it looks like it's storing at our out buffer some data XORed by that. We could check to see some of these functions, not sure what that's doing. This function appears to be very complex, has a lot of sub-functions. If we follow our AES key, it's used only right here. So maybe this is an AES function. We can look back in memory and check out some of these AES functions within tiny AESCC. There's an S box, there's the RS box. There's an Archon. We haven't come across that yet, but I'm guessing that's going to be somewhere. We're just trying to find, we know we're using, there's a good chance we're using 192. I don't think 192 is actually its own function because it's using a extract or abstracted away methodology. Let's see if we can identify some of these functions similarly to how we did last time. Since we're probably doing an AES, probably going to be either decrypt or encrypt, as AES is kind of two-wayed. It doesn't really matter which one you call. I guess it matters which one you call. It just kind of depends on how you call it. But none of them are really lining up well. There is a for loop in both of them. This one has slightly more functions. There's a memcopy, inverse cipher, XOR with IV, so maybe it's abstracting away similarly to last time, where there's a couple functions that we need to, this one's all the exact same, so maybe it's compiling inline, so it's not actually calling these functions, but it's going to just put those functions in line. This one just appears to be a single for loop, so we could try to see if this is a for loop. That's not a for loop. Is this one a for loop? This just to be a direct one-to-one mapping of some sort. None of these should really be for loops. Oh, there's a for loop. It's probably this one then, as it's using the SBox length, using the SBox itself, and just doing a quick index. I'm not seeing any XORs though, so it's probably not XOR with IV. So let's go back, jump down to this bottom. There's a function called cipher. I haven't seen that one yet. Cipher looks a little more interesting. Round key. That's what it's called after it gets XORed with the SBox. It comes the round key, I think. So let's check out this round key function. Within round key, there's another for loop. It should be another XOR though, so it's probably not this one, because this looks to be just a indexing scheme. What about these ones up here? That's just a thunk lookup. That one's just an analysis. These ones all are the same function. Looks like some kind of math. Nothing. Here's another SBox lookup. So we could identify where the SBox is looked up, see if that's used at all. This looks like another rotation of some sort. Just direct indexes. Another thunk, not sure what that's calling. Another thunk. So we haven't identified any XORs yet, so round key might not be great. Actually, that's not true. We did identify some XORs within the function like this. There's XORs in here, but this one's doing it within a for loop. This one's just doing a direct access. But since it's doing it to the state and it's doing a 4x4, that's going to be 16. So there's a chance that this actually lines up with this function. We could further identify it, so it's accessing it through round key. If we go to round key itself, round key is passed in. If we go to add round key, if we go to cipher, cipher should just be passed in with ctx round key, which the round key should just be whatever was identified when we did that XOR loop, or during the init. What about subbytes or shift rows? Subbytes also appears to be a 16, but it's just a direct to get SBox value. We had identified a get SBox kind of index, not that one. This one just does a direct SBox indexing, so maybe this one is subbytes. Subbytes doesn't actually appear to do any subtraction. It's a substitute for the bytes. So let's call this one subbytes. If we go back, we did subbytes. What shift rows? Shift rows appears to be a direct indexing with a shift as well. That could be this one. If we look, it goes 0, 5, 10. This would actually be index 1, 5, 10. Oh, it's also just storing in temp. But since it's doing it based in blocks, there's a good chance that, since there's also 3 blocks here, I think, so 1 block, no, this one has 4 blocks. 2, 3, 4. Does this one have 4 blocks? It should only have 3. Rotate the 3rd row. What about the 4th row? It should be 4 rows. So this one looks very close to shift rows. We're not going to name it yet because it's not fully lining up. This one could also be very close. This one has 4. This one is XORs. This one doesn't have any XORs, so it's probably not that. Mixed columns is another function. Mixed columns has XORs with a for loop. We could just further identify, but all of these are just going to be simple XORs as well. This will be the mixed columns function, I believe. Actually, might be wrong with that. Oh, nope, that lines up because it's mixing all the columns four times. If that is mixed columns, there's a very good chance that the function right above it actually is the shift rows, as that's what's left. Shift rows. We have add round key, which could be happening right here. So maybe that's what this thunk is, because we haven't identified what the thunk happens yet. This function is also called several times without round keys is, once at the beginning, once in the for loop, and once outside the for loop. So let's call this add round key. Lastly, we have one more function that doesn't appear to show up, but if we look at it, it's another shift or XOR of some sort. And I think that has to do with I think that's a part of the add round key. It's actually just done at the end of the round key. Nope. It might just be a part of round key, just the last shift. Could also be with mixed columns, because mixed column was missing I think it's round key though. We also have this function right here, which is another thunk. We're not sure what that's doing. But all in all, this has been lining up very close to the cipher function within AES. So we're going to call that cipher, and we can test to see if this is actually correctly cipherizing or deciphering data with the GDB and some local testing, which is what we'll do probably for the rest of this video real quick, as this video is starting to get longer again. So this is just a wraparound cipher, so there's a good chance that this itself is also cipher. It might just be AESing it in an interesting way. It's weird that there's an AES round key outside of the cipher, but we're going to call this cipher. We can see where cipher's called and see if that's normal. Looks like ECB. Oh, it's right here. There's actually done with a for loop. This one's also done with a for loop. There's a mem copy before, but that's slightly different. But the fact that these are done within for loops lines up with a CTR method. So we might be dealing with AES CTR. So let's actually call this AES CTR. And with that, let's jump in and actually identify if this is AESing correctly. In here, where are we at? We're at 4023 BC. 4023 BC. Should be right there. We know our AES key was initialized with our SHA-256 bytes, I think. Yep. We could go back and grab those bytes, because we're going to do this all by hand pretty much, because we want to make sure everything is correct. The reason I'm just scrolling is because I don't remember us printing the bytes. Actually, we have the SHA-256 right here. We could do this in Python. I wonder if that'll work. Let's try it in Python. If it doesn't work, we'll go to C. When I first did this, I did this in C. I don't know Python AES off the top of my head. Python 3 AES example. Let's open that guy up. Actually, we want AES CTR anyways, so I'm going to do a further search. AES CTR. Looks like we do AES new mode. So it's from crypto, cipher, import AES. I'm not sure if crypto is installed by default, but it might not be. Come to this one. This guy's was wrong, so I'm going to slightly comment out, just see if the library loads. It was not pip3 install pycrypto, I think. Oh, didn't like that. Could not build wheels for required install the library. Why not? Blah blah blah. Well, let's just copy this known module named crypto. I think it's pycrypto. Easy install pycrypto. Don't use crypto or pycrypto. Use pycrypto dome. Pip3 install pycrypto dome. There you go. I think pycrypto was the original, and then it hasn't been updated and had some crypto exploits found against it, or crypto exploits are found and it just works against it. Okay, so it appears to have compiled. We want AES CTR. Assuming this is going to be the key, is going to be set to m.digest. This needs to be a function. The counter is set to the lambda at OS random. Is that correct? So counter within CTR is always set to a value. There are exploits against it if you if you use the exact same key and counter across multiple sessions, but we shouldn't have to worry about that one. We do need to worry about what the key or the counter is. The counter should be stored within the AES structure, which if we go context, should be within X5. X5. It doesn't appear to be. What about X4? X4 appears to be the counter. I think this value right here is the counter. We could identify this by, since we know this is AES, it should be using the counter within here somewhere. So if we use follow param 5, it appears to be using the counter right here at the beginning. So I think the counter is going to be all zeros and then 1. Unless the counter is 16 bytes. The counter is 16 bytes, then it's going to be part of this string as well, which I think if we look back, because that string looks a little bit familiar. Oops, I keep opening the wrong one. There we go. 24A5. 24A5, so it's right here. So it looks to be using some of the bytes from the AES scheme as part of the counter as well. The fact that we know part of the counter, I don't think is an exploit, but it might be. It's probably not safe. The counter is going to be equal to the bytes at m.digest. It appeared to be the 16th to 24th plus the bytes 0, 0, 0 times 7 plus the byte at 0x01. We could have just came over here and dumped out the bytes at this address. I think this is the counter. If we check in GDB again, because that's what's going to be passed in at S5, param 5 is then updated with local C, which lines up very well with what the counter's done. Param 5 plus 12. It's actually only using, it's only updating the last 4 bytes, which I think is right. So I'm not even sure if we need this. I think we just need the last 4 bytes, which is 0, 0, 1. We'll continue on with this for now and see if this works out. Next, since we know it's passing in a buffer, it should be all C's of 190 some characters or something. All C's 195. So if you do crypto.encrypt, the letter C times 195. Turn this into bytes because I think it needs bytes. Go to the Firefox example because they had done something wrong. Secure way you did it. Crypto encrypt. So it looks right. And then if we print out the decrypted, we'll see what we get. Test.py. Missing parentheses. Built-in function object is not subscriptable. So I need to do lambda. Function is not iterable. Function object is not iterable. It should be coming back as a string, so it should be iterable, I think. The way they did it is they used os.urandom, which should just give you characters and secret, so that should be right. Let's put this into secret like they have it. Secret equals, oops, secret equals this, lambda secret, and if we print secret, it should come back as a byte array. It did not like, oh, I need to call that function first. Function is not iterable. Now what function is that doing? m.digest should be on line, this line still. What if we get rid of this lambda and just set secret? Cannot convert dictionary update sequence element 0 to a sequence. I can't tell if that's because of the counter. Just delete that. Set that. Decrypt cannot be called after encrypt. What? What does it mean? I'm name calling encrypt. Oh, cannot be called after encrypt. Oh, that makes sense. Since it's going to mess up the counter. We actually don't need decrypt or encrypt. We're just going to be calling it decrypt. Because our bytes are just the C. C times 195. Object string, we need to pass this in as bytes. Okay, so that's normal. Let's add the counter back. Actually, let's just do default counter and see if it comes up with the same value. This should be the location of the answer. We're just going to step over this function, check it out. It looks like we got A2. I go back to this guy. A2CF, which, let's print this as a hex. Don't need to print the secret anymore either. D5, we do have a 2A. Doesn't look like A2 is in here. Oh, A2. CF, nope. I do A2. Should be at the very bottom. Oh, I did AS, A2. A2 there, A2 there. None of these appear to be lining up, so maybe the counter still needs to be set. Secret. Cannot convert dictionary to sequence. Why is it coming up as a dictionary? It should just be a byte array. What if we did secret.decode? As Latin-5. Latin 0? Latin. Dictionary update sequence 0 has length 2. Lambda at secret. Alright, so somehow they have it set up. They're expecting a dictionary. I'm not really sure how to do that in Python. Do a quick one more Google search. If not, then I'll just pause the video, pause the recording, and then write it up in C real quick, and then walk through what I wrote up. Python 3 AES. Actually, I'm just going to pause the video now. Okay, starting back up. It took me a little bit, but I couldn't figure out the Python example. Probably just missing something silly, but I just wrote it up in C real quick, and this will be easier for future implementations as well. But what we have here is I'm just using the tiny AES library that we had identified earlier. I just git pulled it, and I modified or noticed that their AES CTR excrypt buffer. CTR just uses one kind of encryption standard. It should use the same decrypt and encrypt function within this library. So with this, we should be able to just create our structures. So normally you go AES, create your ADS structure. I'm setting the IV manually to or in this case, the IV is the CTR for AES. The counter and the IV are just implemented in the same, it's like a union pretty much, since depending on what version you're using. So in this case, we're going to set our CTR. Just grab the CTR from memory. The CTR should just be the last or the first 8 bytes of the second half of the SHA-256, the Python, or the SHA-256. So SHA-256 should return 32 bytes. The first 16 should be the IV, or the key, which is this, the C028. The second 16 bytes, the first 8 of that will be the counter, and then it also gets set to 0001. And then the counter increments 1 based on how many bytes you have. So we're going to set the counter in memory. We're going to initialize the counter with the key, because the counter, I don't think the counter needs to be set first, but just did that just in case. Initialize the counter, or the instance with the key should give us the round key in memory. We could go through and print out the round key just to confirm, which isn't a bad idea. Come in here. I'm only going to print out 32 bytes just to make sure that everything's lining up right. We can do this with ctx.round key. I'm not sure if it's capitalized. Just do an exit 0. clear that out, GCC out. Yep. So here's our round key. It's pretty much actually just set to our the round key at the initialize, or the round key is actually a certain mathematical operation where it takes the key and then the first bytes of that should be the key, and then it does lookup and XOR within the S box, and then the next byte should be it. So this should be actually 176 characters long. Maybe I think it should, I think it should be 176 characters long, and the first one should be the actual key, and then it should start changing after that. I'm not sure where it's located. It should be X5, whatever X5 was. I think I already stepped through X5. Let's see if it might have been modified though, because I think the round key gets shifted during operations. Yep, I don't want to run it again, but you just got to trust that this is the correct round key. It might actually look slightly off. The way it's stored in memory is it's going to, actually it's right here. C028E6. It's actually stored as words in this implementation for some reason. So C028E602. It's actually I think it's actually big Indian words, so it's interesting. But that's what a lot of the extra operations that were happening were. Is there's a lot of conversion back from big Indian and little Indian, so we don't really need to worry about that. But if we continue through, we just created a temporary encrypted instance, set it all to C's, in this case 195 of them. Then if we decrypt it, just decrypt straight back into that memory. So I'm going to print out the first 32. As long as the first 32 are correct, everything else after should be correct, assuming your round key is correct, as CTR just continues based off of that instance. Running it, we get A2, C1, A1. In this case, we got A2, CF, A1, 0D, DE, 2, 3. So it looks like we did correctly get this to print. We can see that within the instance where it gets returned. It's going to do 16 bytes, so it goes byte at a time. So there's nothing too crazy here. We just identified that this function is just doing normal AES CTR stuff. Initializes it with the round, or our key, in this case the SHA-256. The only interesting part that you really need to keep track of is that the counter is also using the SHA-256 instance or value. And the fact that we took note of that means that we were able to get the correct SHA or AES value outside. I think that should be it for this video. We have a couple more functions to analyze. They shouldn't be too bad to look at. They're kind of all the same or similar structured. But after that, then we will hop into actually identifying the vulnerability with this code, and then should hopefully be able to exploit it in the same video. Otherwise, thanks for watching.